right, hello everybody. So we're going to talk a little bit about directions for the Java language. I'm Brian Goetz, Java language architect. And there have been a lot of talks, and will be a lot of talks at JavaOne this year about various aspects of the language. There's a talk later on pattern matching. So I'm going to try to keep this as sort of a higher level overview of like where are we going, and more importantly, why are we going there? So one of the questions that people ask us a lot is, how do you decide what to work on in Java? And there's an infinite number of things that we could be working on, and people want us to be working on all of them at once. And we try to pick on the basis of, first of all, only the things that only we can do. And second, the things that we see have become pain points for many different categories of developers. So people are very eager to share their pain points with us, which is great. And we kind of then try to take in, a holistic view of what are the things that are hitting people in various places. And then we do our work inside of these, what we call projects within OpenJDK, where each project has a theme. And in general, each project is oriented around a pain point we've observed, a direction for addressing that. And usually these are, one can always point to competitive situations of, oh, that language does this better, this language does this better, right? So I clearly can't talk about all of these. I'm going to talk about two of them. One of them is Project Amber, and the other is Project Valhalla. So Project Amber is, in some sense, one of the more misunderstood projects that go on in OpenJDK. So there are some projects like ZGC that are very focused about delivering a single feature, the ZGC garbage collector. Project Amber is kind of all over the map. It has a very broad remit, which we call right-sizing language ceremony, which is basically all of the things that make developer productivity just a little bit better. And this, is, like I said, it casts a broad net. It captures small syntactic-focused features like local variable type inference, and also more fundamental features like pattern matching. We deliver things in small pieces, in individual JEPs. Our goal is for each individual JEP to both stand on its own, but also to be part of a broader multi-year story. Some JEPs are more, standalone than others, but a lot of JEPs are things where we designed several features together and then deliver it as part of 2 or 3 or 4 JEPs. So breaking a big feature down into smaller deliverables has some advantages and some disadvantages. Obviously, if we're delivering smaller, they're easier to understand, easier to absorb, fewer new concepts, we can deliver sooner. On the other hand, it can make it a little bit harder to see where we're going, so that's why I'm here. So here's a list of JEPs that have been delivered, not counting preview JEPs. This is just finalized JEPs that Amber has delivered over the last 14 versions. And they're kind of all over the map, like I said. And some of them, like local variable type inference or text blocks, are very focused, narrow features. And some of them are pieces of a larger feature arc. So one of the feature arcs and that I'm going to talk about today is the records and sealed types and pattern matching feature arc, which so far has spanned, I guess, 7 JEPs so far, and there's more coming. Another feature arc that you might have been able to notice is the just making it easier to get up and running with small programs, which includes the source launcher, module import declaration, simple source files, et cetera. And so again, each of these are self-contained features, but they were designed together with some other features, and they are part of a bigger whole. So let me do a little bit of a recap of some of the things that we've done recently in Java, especially on this feature arc for pattern matching that I was just talking about. Now, you're all familiar with records. Records have been around for a number of releases now. And they were sort of the first piece of this bigger arc, which is records, sealed types, and pattern matching. And the story is not yet done, but it's in a pretty good place right now, and it's at a place where we can sort of gather some of the threads and see where, see why it is that we chose these features and worked on them together. And so for each of the features in this arc, they have a kind of a double meaning. One is a very local, they're directly addressing a pain point, but the other is being part of the bigger story. So a record is a nominal tuple. You declare a record by saying record, and then the name of the record type, and then a list of components. And it, on the one hand, is just a shorthand for a class that's a simple data carrying class, but it's a real class. Those brackets after the record header are a real class body, and you can put methods there and constructors and static fields and things like that. But most of them are empty because we derive the implementation and the API of a record from its state description. So we call these shallowly immutable data holder classes, which is kind of a mouthful, but it kind of says what it does. We take the state description, which in this case is first name, last name, and we derive the implementation from that, the representation, the fields, the API, and the implementation of that API, constructors, accessors, object methods, and as of somewhat later, also the ability to deconstruct records with record patterns. Now, when we started on this project, there were a lot of competing ideas about where we should go. You should do properties, you should do tuples, you should build Lombok into the language. And those all have pros and cons. Some of them have more cons than others. But the design center that we picked has a lot in common with the design center that we picked in another major evolution of Java, which was lambdas. Back when we did lambdas, everyone is saying, oh, what Java needs is structural function types. And what we actually did was nominal function types, functional interfaces, because names matter. Names make our programs readable. When I say record name, string first, string last, I'm giving a name to the abstraction. I'm giving a name to the components of the abstraction, rather than just saying it's a pair of two strings. A pair of two strings could be anything, but a name has more meaning. And so we did this with behavioral abstraction in Java 8, and we did this again with records in Java, I guess, 16, because this is building on how Java works. So what records aren't? There's a lot of things they aren't. They're not a syntax generator. They're not a replacement for Lombok. The purpose of adding records to the language was not just to reduce the boilerplate, although that's a very nice side benefit that we got. The main goal is to give people a clean semantic way to model data, to say a name is a first name and a last name. And that's a semantic statement. In fact, like if you read the specification of Java Lang record, which no one ever does, you'll find that like you've actually signed up for some constraints that you might not have been aware of, that it should be possible to take a record apart with its accessors, feed the results back to a constructor, and get something that's equivalent to what you started with. And that's another way of saying a record is the state, the whole state, and nothing but the state. So one of the things that makes it possible for records to deliver all these goodies without collapsing into a morass of configuration options is that you're giving up some flexibility. You're giving up the ability to like design an ad hoc API around your data. The API you get is the API that's implied by your data, and if you accept that constraint, you get a bunch of benefits from it. One of the features we did right after records was seal types, seal classes, which is a generalization of finality where a class can say, here are the subclasses that can be my direct subclasses and nothing else. And this is enforced both by the language and by the VM. So it's kind of like not quite final, but almost final. Final means nobody can extend me. Seals class means these 5 guys can extend me. You don't actually have to write out the list of subclasses if they're all declared in one place, which is convenient. And it's possible to open up subclasses for extension if that makes sense in your domain. Why do we do this? Well, a number of reasons. One is it makes it possible to build more secure APIs, because it means you can declare an API that's defined with interfaces, but control all the implementations, and therefore reason about all the implementations, which isn't something you can do if anybody can come along and maliciously implement your interfaces. As a bonus, it also becomes a source of exhaustiveness information that the compiler exploits during pattern matching. So if you put these two things together, records and sealed types, you get a whole is greater than the sum of the parts thing. So just borrowing some potentially obscure technology from the functional programming world, records are an example of what we call product types. Product types are just Cartesian products, one from column A, one from column B. And that's what a record is, right? First name, last name, pick a first name, pick a last name, that's a Cartesian product. Another way to say that is, a name is a first name and a last name, with the emphasis on and. Sealed classes are sort of the dual of that. They're sometimes called discriminated unions or sum types, and where records are about and, sealed types are about or. A shape is a circle or a rectangle. And the combination of sum and product types is what are called algebraic data types, which is an unnecessarily complicated term, but it turns out that this is a phenomenally powerful mechanism for modeling data in a great number of domains. And so once you have these two basic mechanisms in your language, the ability to model aggregation, the ability to model choice, it turns out that most data domains are well described by sums of products or sums of products and things like that. And once you sort of learn to spot that, you can't unsee it. And it has the effect of making our APIs simpler. So as a kind of extreme example, if you read the JSON spec, you'll see diagrams like this one that says a JSON value is either a string or a number or an object or an array or one of these constants. And that's an algebraic data type. The simple ones at the bottom are kind of like enum constants. The ones in the middle, like object and array, those are like records in the sense that like an array has an array of elements or a list of elements. An object has a map from string to values. And so if you look at this, this is an algebraic data type, and it kind of suggests a very obvious way to model JSON in an API, which is this. We're going to have a sealed type for JSON value. What's a JSON value? It's one of those 7 things. That's what the spec says. What are the 7 things? Well, each one of them is a record. What do each one of them have? Well, just look at what the JSON spec says it has. A string has a string. A number has a number. An array has a list of JSON values. And so you've always been able to do this in Java, but there's always been a lot of boilerplate in the way that makes it harder to see this. And once you see this, you find that designing APIs becomes, for want of a better term, a less creative activity because the data domain is dictating your design for you right there. You just have to see it and model it directly in code. So maybe a nicer way to say this is it has a normalizing effect on API design. So the last feature I want to talk about that's part of this arc is pattern matching. And pattern matching is a lot more complicated because it has a lot more different aspects than those two. So the simplest form of pattern match is a conditional extraction. You have a snippet of code here at the top where I say if x instance of string s, what does that mean? If x is a string, then cast it to a string, and then take the result of casting it to a string and bind it to a new variable called s. So those are 3 things that we do together all the time in our code. Pattern matching turns them into a single fundamental operation that you can't misuse. Right now, if you have to say if instance of and then cast, well, having to do something twice or 2 different ways is an opportunity to make a mistake, in addition to being more code than you want to say. So pattern matching gives us a concise mechanism for conditional extraction. And it's also, the example up here is a very simple kind of pattern match. You can also have much more complicated patterns, like, are you a record? If so, cast yourself to that record type and extract all the components and bind them into variables. And there's other kind of patterns that are coming. So I'll give some examples of how this works in a second. But one of the things we had to do along the way to make all this work is there were a number of language features that we kind of had to give a facelift to. So we had to give a facelift to variable scoping, and we had to give a pretty big facelift to switch. So switch was originally extremely limited. You can only switch over certain types. The case labels could only be constants. It could only be a statement. You didn't have very good exhaustiveness checking. And we were able to eliminate almost all of those restrictions. And now you can switch over any type. Your case labels can be patterns, which are much more expressive. They can have guard clauses. You get much better exhaustiveness checking where the compiler will type check for you that you've covered all the cases. It can be an expression versus a statement. So one of the reasons why this particular feature took longer than you would have thought is we had to fix up a bunch of things along the way. So let's do a slightly more complicated example. The standard computer science textbook example of modeling an expression, where you can say an expression is the sum of 2 expressions, or the product of 2 expressions, or the negation of an expression, or a constant. right? And whenever you see something defined in terms of choices like that, you should be thinking sealed types, algebraic data type. Everywhere there's a choice in your domain, that's a sealed type. Everywhere there's an abstraction in your domain, that's a record. And I can model this as a sum of 4 product types very straightforwardly. It's not a lot of creativity went into that, right? And if I want to evaluate that, that expression, well, my evaluator is probably going to have 4 parts to it because there's a choice of 4 things, and switch is our mechanism for implementing choices. And so the code for evaluating that expression is pretty straightforward. I switch over the expression. If it's a sum, then I get the left value, the right value, evaluate them, add them together. This code is really very straightforward. I don't have to explain it. So what you're seeing in this example is I'm using type patterns in the switch statement to say, are you a sum expression? And then I get the expression cast to a sum expression, and then I can access the left and right sub-expressions. But I can actually do that a little bit more neatly using record patterns. So this is the same code, except that I've changed the type patterns in the bottom to record patterns. The thing after the case keyword is a record pattern, and it's saying, are you a sum expression? If so, cast it to a sum expression, extract the left and right sub-expressions, and put them in A and B. And then the thing on the right-hand side of the arrow got simpler because I had already extracted all the bits I needed from my record, and now all I have to do is operate on them. And this is, the var pattern is actually a pattern. It's not actually just a variable declaration. What happens is it's recursively taking the left component and trying to match it to the pattern that's specified in the parentheses there, which in the case of a var pattern is just match everything and stick it in the variable. Okay, so this is a nicely composable mechanism, and you'll see some more complicated examples in a second. So going back to our JSON example, if I had written a JSON API using those 7 record types and a sealed type, and I wanted to match against a document and extract some bits out, if you try to do this with like a traditional DOM API, you have a million checks of, is this thing a JSON object? If not, fail. Does it have a key called name? If not, fail. Is the name mapped to a string? No, fail. Okay. Get its value as a string. I'm going to put that somewhere under the rug. And then I repeat that dance like 70 more times. And I can't find my domain code in the midst of all of this format checking. Expressing this with pattern matching allows what's going on to become much more clear. So I have this, this big Boolean expression that says, is this thing a JSON object? If so, extract its key value pairs. And does it have a key called name? And is that thing mapped to something that's a string? If so, extract its string and put it in the variable called name. And so each of these lines of code embodies 2 or 3 or 4 of those. Does it have this? No. OK, fail. Logic that we would have had to do with a more traditional DOM-based API. And so the code is a lot less error-prone. It's also a lot more clear what's going on. What parts of this document do you care about? What assumptions are you making about this document? That the outside thing has to be an object. It has to have keys called name, age, and city. They have to be bound to things of a certain type. And then you get the bits out you want, and you leave the JSON object behind. So there's kind of a lot going on here, so I want to make an analogy about the relationship between patterns and expressions. If I have an expression, like creating a new sum expression, the values flow from the inside out. First, I'm going to evaluate E1 and E2, and then I'm going to pass those to the constructor of sum expression, and that's going to give me a new value, and then I'm going to stuff that into the variable E. Right? And so you can sort of think of the values as flowing from inside out. You evaluate the innermost thing, and then you do a bigger thing, and they propagate outward. In a pattern match, it works exactly the opposite. So if I say, is E an instance of some expression, and then if so, unpack it into its left and right components, the data is flowing from E into the sum expression pattern. And if that matches, some new data flows out, the left and right sub-expressions, and that flows out into the patterns var A and var B. And if we put another pattern that was maybe more selective in place of var A or var B, the whole process would repeat one more layer. So Patterns and expressions are deeply related. They're kind of the opposite of each other. They get one gets evaluated inside out, the other gets evaluated outside in. So, as an example, what I was saying about nesting one pattern in another. So if I have a record for point and I have a record for circle, and the center of a circle is a point, and I want to say, does this thing match a circle? And then I want to, if so, get its center and its radius, and I want to take apart its center into x and y, I can nest the record pattern point var x var y inside the circle pattern. And so this is saying, are you a circle? If so, cast it to a circle, extract the center, now try to match it to that pattern in blue, which says, are you a point? OK, great, you are a point. Cast it to point, extract the x and y, and then stuff them in these x and y variables. And so patterns compose the same way as expressions, which is, makes it possible to build more complicated queries, like on our JSON example, in a more concise way. OK, so that's all really cool. What's the point? Well, the point is that we want Java to be better at dealing with data. And if you look at Java's history, Java is an object-oriented language. It started in the 90s when object orientation was going to be the thing that cured cancer and all of that. And the problems we were solving in those days were largely about modeling complex entities and processes. And OO was really good for that, because OO gave us a tool for drawing boundaries and saying, like, inside this boundary, it's a black box. And outside, I'm going to commit to this, this API. And that allows us to manage complexity by dividing it into pieces. Well, what is OO bad at? OO is bad at modeling data. And 30 years later, the programs we're writing have changed. We're writing smaller programs. We're writing services that get their inputs as plain data, maybe from programs that aren't written in Java. And they come in as untyped JSON or XML blobs, and we have to validate them and extract the bits we want. And we don't want to work with them in that form. We want to work with them as Java data. And so if Java's strong suit was modeling complex stateful entities, and its weak suit was modeling data, well, that's not as good of a match for today's programs as it was for the programs of 30 years ago. And so if that's shifted, we want the language to shift as well to be better at dealing with plain old data. And so each of these features is about plain old data. Records are about modeling aggregations of data. Steel classes are about modeling choices about data. Pattern matching is about taking apart these aggregations in a natural way. So we've kind of thrown around this phrase data-oriented programming, to describe the process of starting your design from your domain data model, modeling it using the dumbest possible API, using these very regular language features, records and sealed types, and dealing with it in that form. The story's not finished yet, but we're at a point now where these features do a good job at the boundary of systems where you get untyped, unvalidated data coming in. At the boundary, you want to do your validation. You want to extract it into actual Java data types. You want 32-bit ints. You don't want numbers that are just like big strings of digits. And then deal with them inside your program just in the form that you want. So that's all pretty cool, and that is something you can use to make your code better today, but there's a bigger story here. And so I want to talk a little bit about where that's going and why. So Java is full of features that abstract away things or throw away details. And we like it that way, right? A constructor takes a bunch of arguments and gives you an aggregation. And can you get those values back that you passed to the constructor? Well, maybe. Maybe if the class exposes accessors for them, you can. Or if you implement a method that's supposed to return a list and you say return new array list, we do that all the time, right? But when you return it from the method, you're throwing away the detail that it's an array list and not just a list. And in general, there's no one-size-fits-all way to recover from this loss of detail, although often we try to bake that back into our APIs in these ad hoc ways. And pattern matching offers us a sort of more principled way of recovering from detail loss through abstraction, which is inherently conditional because it's always about asking questions. I have an object. Is it really a string? If so, give it to me as a string. I have an object. Is it a point record? If so, give it to me as a point record and give me the x and y components. I have a double, but is it a floating point value, or could it be encoded exactly as an integer? If so, give me that integer value, right? So pattern matching allows us to ask these questions in an organized way. So it becomes safer to use these abstractive mechanisms and define the situations under which we're going to be able to recover from that loss of detail. One thing that you may or may not have noticed, if you look at the syntax for record patterns and record constructors, they look an awful lot like each other, and this is not an accident. And that's because they're two sides of the same coin. One is putting something together into a larger whole. The other is taking that whole apart and getting back its constituent components. And right now you get this for free with records, but eventually any class will be able to declare deconstruction patterns just like they declare constructors today. And then eventually you'll be able to do the same thing with static factories. And so if we construct something with a factory rather than with a constructor, there will be a corresponding pattern form that, again, just accidentally syntactically resembles the factory syntax. So we're able to derive a lot of good stuff from records automatically because we've made the commitment that a record is its data. And so we get constructors and pattern matching and accessors and all of that. But we'd also like that to just be sugar for something that you could have written as an ordinary class yourself. And so eventually, you will be able to declare deconstruction patterns in a class alongside the constructor. And if you look at sort of what they look like, so a constructor says, I'm the constructor for point, I take x and y, and then what do I do with that x and y? I stuff it into the state of the object. Its dual is a deconstruction pattern for point, and it kind of looks like x and y are parameters, but like I said, pattern matching, everything is backwards, and so the x and y parameters are really output parameters. I'm the deconstruction pattern for point, and I give out an x and a y. Well, where do I get that from? I do that by looking at the state of the object. And so these two things are mirror images of each other, and it allows us to enforce abstraction boundaries and validate inputs and all of that without suffering the and now I've thrown away all my detail, because the detail is still recoverable, but in a organized, mediated way. And so, like, when I declare a constructor, the parameters are inputs. When I declare a deconstructor, the parameters are outputs. And the fact that these two look syntactically similar is also not an accident, because they're two sides of the same coin. Putting something together, taking it apart. So we're going to keep playing this game. We have lots of ways for aggregating in the language. We don't have such organized ways yet for taking things apart. So if I have an API for shapes, and I've got a factory that says, make me a sphere that's colored red and whose radius is 1, and now I want to wrap it in an optional. Well, it's so easy you don't even notice that there's anything going on there, but the optional factory and the ball factory don't know anything about each other. They just compose naturally. I run one, and then I feed that to the other. Now, if I wanted to run this in reverse today and ask, does this optional shape hold a shape that is a ball whose color is red and whose radius is 1, I have to write this monstrosity, right? And I'm using an ad hoc API from optional to take the optional part apart, and then a different ad hoc API from shape to take the shape part apart. And I see a bunch of you looking at the code, right? And the reason you're looking at the code is it's not obvious that that code does the right thing. You have to actually read the whole thing and say, oh, OK, yeah, it does the right thing. I wish I didn't have to read all that. What we would like to get to is being able to say, when I want to take the ball apart, is to be able to express a pattern that looks just like the construction. To say, is this thing an optional? If so, does that optional contain a ball? If so, is the color of that ball red and its radius 1? And either the whole thing is true or the whole thing is false. So we would like to get to a point where taking things apart looks like putting it together. That's kind of the big goal for pattern matching. So there's lots more work to do. There's more pattern matching JEPs coming. We've been trying to do it, in order not only of most immediately useful, but also least conceptually challenging, so people have a chance to get used to the concepts before we move on to more complicated ones. But there's a bunch of work, in the pipeline here. Now, one of the places where this is going to be used very soon is in the work that we're doing to provide a more sane alternative to serialization. So I wrote a paper about 5 years ago called Towards Better Serialization, which you can find on the OpenJDK website. And Victor and I talked about this at DevOps this past November, where we outlined an approach for making serialization safer by allowing the class author to provide the mechanism for converting an object to its at-rest form and back. And the mechanism for doing that is constructors in one direction, deconstruction patterns in the other direction. And what that enables is when objects get reconstructed through deserialization, they go back through their constructor that can validate their arguments. The reason why serialization is full of so many security holes is that we're creating objects by just taking this untrusted stream and scribbling those values into memory. And so they may not be valid values. They may not conform to the invariance of the class. And so if we can deserialize by going back through the constructor, we can make the whole process not only more scrutable, but also more secure. And this is something that builds directly on this work to add deconstruction patterns to the language. And so having this mechanism is not just about writing better code for taking things apart. It's about writing better frameworks for dealing with objects. So lots of cool stuff going on in Project Amber. I want to talk briefly about Project Valhalla, and I'm going to probably have to talk fast because running out of time here. But you've probably heard about me talking about Valhalla for the last 10 years, and you're probably wondering, yeah, that's going to happen. And the reality is, this is a huge project. People have called this Java's epic refactor. It touches basically every layer of the platform. But the good news is we're almost there. We're hoping for the first JEP is in early access now. We're hoping for it to be in preview in the fairly near future. Big goals for Project Valhalla, and they are big goals: flatter and denser memory layouts for Java object graphs, unifying the Java type system so that primitives and objects are not these diametrically opposed things, and enabling new numeric types to be added to the platform as libraries rather than as new primitives. So big goals, big project. But we kind of boil it down to the little slogan, codes like a class, works like an int. Now, the JVM spec doesn't say anything about how objects should be laid out in memory, but if you read between the lines, there's really only one choice most of the time, which is to map object references to pointers and objects to blocks of memory like we do in C. So if I have a point record and I have a rectangle record that has 2 points, and I say make me a rectangle with these 2 points, I end up with a layout. I'm likely to end up with a layout something like this, where each of those, where the rectangle is a block of memory on its own, and the 2 points are pointers to other blocks of memory, and those blocks of memory hold the x and y values for my rectangle. And that's perfectly fine, it works, but it's not necessarily the best match to today's hardware, where memory indirections can be expensive. And also, this is using a lot more memory than a more compact representation might. So a more compact representation might look like this, where there's just one object for the rectangle. We flatten out the x and y points and just allocate them all in one place. In some cases, like the more expensive layout doesn't matter, it's fine. And in some cases, it does make a very big deal. Indirections mean cache misses can be expensive, and over the past 30 years, the relative cost of cache misses and computation have diverged tremendously. So basically the question Valhalla asks is, under what conditions can we make it possible to enable the JVM to give us this layout instead of the previous layout? And you could ask the same question about arrays. Arrays typically are an array of pointers. Each pointer points to an object with an object header and a payload. And we can ask the same question for arrays. Under what conditions would we make it possible to lay it out like this instead? And is it possible to do that without completely turning the language into something that it's not? So this is the question, the memory flatness and density question that Valhalla has addressed itself to. So there's a lot of reasons why we're kind of locked into the layout that we have. Objects have identity. Identity means effectively that an object has to live in one unique place, and that means we have to represent references to it by pointers. Nullability is also part of the story in kind of surprising and subtle ways. Object initialization is also part of the story in surprising and subtle ways. It's a little bit like the Spanish Inquisition sketch, because we started out thinking, oh, the big problem is identity. Identity and nullity. Identity, nullity, and initialization. Identity, nullity, initialization, and integrity. We kept discovering that there were more impediments to density and flatness than we thought. And so it took a while to chip away at all of those. Now, density and flatness is one goal. Another goal is unifying the type system, making primitives and objects more like each other. And this is kind of crazy on the surface, because if you make a big chart of things that that are different between primitives and objects, the answer is everything, right? They're different in almost every possible way. And so why do we do this? And you can think of this as Java's original sin, right? It's something we had to do in 1995 because it was the only way to get reasonable numeric performance. It seemed like a pragmatic engineering compromise, and it wasn't so bad. We lived with it, but it got worse over time. In Java 5, it really affected the design of generics, and it meant that there were certain types you couldn't generify over. And then in 8, it got worse again when we had this explosion of hand-specialized functions like int-to-long function and things like that. And so this seemingly pragmatic compromise in 1995 has grown to have greater and greater impact on the code we write. About 80% of the code in the Streams API, for example, is for dealing with primitives and having different versions of streams for different shapes of data. It would have been so much easier if we didn't have to worry about that when we were writing that. So primitives are largely a performance hack. They're a way of getting flatness and density because they just happen to have all the properties, like they have no identity and they're not nullable by default and all of that, that make it possible for the VM to deliver flatness and density. But there are other numeric types we'd like to have in the language too, like 16-bit floats or complex or decimal. And we don't have an easy way to add those in a way that behave like the primitives we have today. So, like I said, they differ in every possible way. One has members, the other doesn't. One has polymorphism, the other doesn't. One is nullable, the other isn't. One has identity, the other isn't. So, how the heck are we going to unify these things? And it took us a while to figure out how we were going to do this. So, interestingly, after all of this churning, it turns out that the intrusion into the language surface that we need to address most of this is actually pretty small. So you can think of it as adding two simple, in air quotes, features. One is value classes, which are classes that disavow their identity. And the other is the ability to control nullity by saying this is a non-nullable string, this is a nullable string. So simple, right? How could that take 10 years? The latter one is something people have been asking for anyway, completely outside of Valhalla for quite a while. So it's kind of a nice bonus that with two birds and one stone. Okay, so let's talk about these features. Value classes. This is the first JEP that's coming, JEP 401. They're classes that give up object identity. And that means that you're giving up all the things that object identity enables, like mutability. But not all classes are mutable. Or intrinsic locks. Not all classes use intrinsic locks. So there's a lot of classes out there that don't need their identity. And for those classes, they actually don't want it. The identity is actually just a mistake waiting to happen. If you give up object identity, you're basically giving permission to the VM to freely copy these things, take them apart, put them back together, however it sees fit. And so, for example, when I pass a value point to a method, what the VM is likely to do is not put an x and y in a memory cell and pass a pointer to that. It's just going to put x and y in registers and call the method. And what that enables is something kind of subtle, which is the fact that we can do things with immutable idioms like records and have them be as fast as mutable objects, which is really kind of cool. So we get all of the abstraction and safety benefit of immutability without paying a performance penalty for it. So the only syntactic intrusion for value classes is this value modifier on the front of the class. And then what that means is the class itself is final, the fields are final, there are a few other restrictions, they're actually pretty minor, and it means that the equals operator compares two objects not by their identity, but by their state. Are these 2 points the same? Well, do they have the same x? Do they have the same y? That's what equality means for value classes. And so, we've all written classes that are good candidates for being value classes. A lot of us just didn't know it. But it doesn't take very long to recognize, oh yeah, that should be a value class. And just like with finality, it took us a while to realize that if you can make something final, you should make it final, because you're giving up a degree of freedom that's only going to get in your way. It's only going to cause subtle bugs. Identity is the same kind of thing. If you don't need identity, don't use it. And then you're giving, you're making a semantic statement, makes your code clearer, and also VM can optimize it more effectively. So when would I declare a value class? Why would I declare a value class? Well, basically, whenever you're declaring a class that is just its state. You don't need the things that identity gives you. You don't need mutability. You don't need layout polymorphism. You don't need cyclic representations. You don't need locking. And obviously, there's some classes that need those things, but there are a lot of classes that don't. And like I said, if you don't need a certain degree of freedom, probably best to give it up because it makes your class simpler and it makes your code more optimizable. Records and value classes go really nicely together. Records are not going to be automatically value classes, but most records can be, and so you can say value record to get the benefits of both recordness and valueness. And we spent a lot of time making it possible to take a class that meets all the requirements for being a value class today and migrating it compatibly to be a value class tomorrow. So classes in the JDK like local date or integer are going to be value classes in the future. And so programs that use those classes, of which there are many, just automatically get faster. So on the topic of faster, our philosophy is that optimization is the purview of the JVM. We should write clean code that says what we need it to do, and ideally give people tools to write that code in such a way that the JVM can optimize it effectively. So the language model is about program semantics, not about performance. So there's no flat keyword of take this object and flatten it. We let you give up the things that are impediments to flattening, and the VM figures that out along the way for you. So last feature is null restriction. Some of you may have seen this in Scala or Kotlin. It's commonly using the syntax of question mark for nullable and bang for non-nullable. That syntax actually comes from regular expressions where it denotes cardinalities. Nullity turns out to be a flatness and density hazard, but it's also a safety hazard. Not all code wants nullability. Not all code needs nullability. And when you don't want something to be null, having it be nullable is a place for bugs to hide. If you can say exactly what you mean, this thing is non-nullable, then the compiler can type check your program more effectively, and the runtime can detect failures more easily. So null restriction is a popular feature from other languages that people are constantly asking us for, which we might be able to separate out as a separate delivery or deliver with the rest of Valhalla. We're not exactly sure what the schedule is going to come out to be. But again, a key part of our design goal for this feature is make it so that adding nullity information to an API is binary and source compatible, because otherwise people would never add this information to any of their APIs. And so that results in a language that's slightly different than what some people might expect it to be, but we care a lot about migration compatibility, and so we've chosen the thing that makes sense for the Java ecosystem. So there's a bunch of JEPs on the roadmap. Some of them have numbers, some of them don't yet have numbers. JEP 401 is the first piece. It's basically value classes, and that's it. And that is well underway. The spec has been stable for over a year. We're just polishing the implementation. There's a second early access coming out fairly soon. And then looking a little farther down the road, there's null restricted types as a concept on their own. There's null restricted types in the context of value types, which adds in some interactions and optimizations. And then there's sort of a cleanup JEP to sort of minimize the gap between the legacy primitives and the null restricted variant of their box types. And I'm sure these are not going to be the only 4. So this was a very quick sketch of Valhalla. I know I spoke fast and glossed over a lot of things. There's a much more detailed talk that I did at DevOps this past November. So if you Google for Valhalla, where are we, from DevOps 2004, you can get a lot more information. And with that, I have 30 seconds left to take questions. Good timing. All right. One question, maybe? We can take one question before they kick me off stage, which has happened. First row.
Whatever happened with the whole discussion about tiering and...
Yeah, so the question is, gee, I've been reading the Valhalla list, and I've been seeing a lot of angst about object tearing, and loosely consistent objects, and what do we do when we try to flatten objects that are bigger than the atomicity threshold of my hardware? We're still working on that. So that's not on this roadmap that I just talked about. That's stuff that we're continuing to work on to be able to enable better performance for larger value types in the future. So, all right, and now we are out of time. Thank you very much.